Okay, this video is going to review the procedures for testing hypotheses using the z-test. Remember from class that we learned how to test both one-tailed hypothesis tests as well as two-tailed hypothesis tests. And the difference is that with a two-tailed test of the hypothesis, the problem doesn't specify that the difference needs to be in a particular direction. So if you look at the null hypothesis there, it says the mean of the group is going to be equal to the mean of the population, but the alternative hypothesis says the mean of the group is simply different from the mean of the population. If we come over to the one-tailed test over here, we have two varieties, and it all depends on whether or not the problem indicates that the expectation is for the mean of the group to be lower than the mean of the population, in which case these hypotheses pertain to that problem, or if the problem specifies that they expect the mean of the group to actually be greater than the mean of the population, in which case the second set of hypotheses apply. So looking at this, we have the two-tailed test, which is no difference specified. We have the one-tailed test, which shows that either we can expect or predict that the mean of the group will be less than the mean of the population, or the mean of the group will be greater than the mean of the population. Also remember that values associated with alpha, the critical values associated with alpha, change depending on whether or not it's a one-tailed or two-tailed test, and also whether or not it is an alpha level of 0.05 or 0.01. Remember in class, I drew the table where we had the one-tail and the two-tail test. Oops. And then we had 0.05 alpha level and 0.01. And if it's a one-tailed test, then the critical value is going to be 1.65. That's going to be either plus or minus 1.65. If it's 0.01, the critical value will be either plus or minus 2.33. For a two-tailed test and an alpha level of 0.05, the critical value will be plus and minus 1.96. Both values are used during that calculation. For an alpha level of 0.01 with a two-tailed test, the critical values will be plus and minus 2.58. So hopefully you have that table in your notes. It should come in handy during practice problems and also for the test. These are the two formula that we need to evaluate hypotheses, and we use both of these each time we do it. It doesn't matter if it's a one-tailed or two-tailed hypothesis test. So our formula for Z says that in the numerator we take the mean of the sample, which is x bar, and we subtract mu, which is the mean of the population, and we divide by standard error of the mean. Okay, and then standard error of the mean, which is calculated down here, becomes the denominator of the Z ratio. But the calculation of standard error of the mean says take the standard deviation of the population and divide by the square root of the sample size. So the calculations are very straightforward. This value that we calculate up here is the calculated value of Z. In order to reject or fail to reject the null hypothesis, the calculated value of Z is going to be compared to the critical value of Z. And the critical value of Z is what we talked about in the preceding slide. What is that critical value that's determined by the alpha level, either 0.01 or 0.05, and by whether or not a two-tailed or one-tailed test is being asked for. Let's work a problem. I've taken this from page 278 of the textbook Graviter and Wallnow 8th edition. It says Monterello and Martins found that 5th grade students completed more math problems correctly when simple problems were mixed in with the regular math assignments. A researcher selects a standardized mathematics achievement test that produces a normal distribution of scores with a population mean of 100 and a population standard deviation of 18. The researcher modifies the test by inserting a set of very easy problems among the standardized questions and gives the modified test to a sample of 36 students. If the average or mean test score for the sample is x bar equals 104, is this result sufficient to conclude that inserting the easy questions improves student performance? Test with an alpha level of 0.05. Over here on the right, I've got my alpha level specified, and I've also indicated that it's a one-tailed test. The reason that it's a one-tailed test is because the problem asks if this improves student performance. Okay, see that right there? If it improves student performance. So it's asking for change in a particular direction. In that case, our null and alternative hypotheses will be as follows. Okay, if the question asks if inserting these easy problems improves student performance on the test, then we would expect the mean of the group to be greater than the mean of the population on that test. The null hypothesis has to be the opposite inequality plus the possibility that the mean of the group and the mean of the population are equal. So that lays out the hypotheses for a one-tailed test. Because the alpha level is 0.05, our critical value of z is going to be equal to plus 1.65. The problem specifies or predicts that the mean of the group should be greater than the mean of the population. That leads us to formulate the alternative hypothesis this way. But it also necessitates that our critical value for rejecting the null hypothesis be plus 1.65. Looking at the remainder of the problem, we see that the sample size is 36. The mean for the group that got these easy problems thrown in to the mix of the test was 104. The population mean is 100. Okay, so typical performance on this test is to earn a score of 100, and then the standard deviation of the population is 18. So we'll go to the next slide and see if we reject or fail to reject the null hypothesis. Let's walk through this problem. Up here at the top, I've just recreated the elements of the problem: the sample size, the mean of the group, the mean of the population, and the standard deviation. These are my hypotheses. My null hypothesis is that the mean of the group is less than or equal to the mean of the population, and my alternative hypothesis is that the mean of the group is greater than the mean of the population. My my alpha level is 0.05, which means that my critical value for rejecting the null hypothesis is going to be plus 1.65. We went over all that during the previous slide. So if you look down here at the z calculation, in the numerator we have the mean of the group minus the mean of the population, 104 minus 100. And we have to divide by the standard error of the mean. We don't have that, but they've given us the population standard deviation as well as the sample size, and that's the only two things we need to calculate the standard error of the mean. So we simply put the standard deviation in the numerator, 18, take the square root of the sample size, which is 36, and that leaves us with 18 divided by 6 for standard error of 3. Now, if we take that 3 and plug it into the denominator of our ratio, we see that our calculated value of z is 1.33. And that calculated value has to be compared to this critical value of plus 1.65. And it has to be greater than that value in order for us to reject the null hypothesis. But it isn't. So in concluding this part of the problem, we have to say that we fail to reject oops, the null hypothesis. The meaning of this result is that the inclusion of these easy test items in the achievement test doesn't have an effect on how well people do on the test after all. So making this change or adjustment to the test doesn't seem to affect the outcome at all. In other words, we failed to reject the null hypothesis. The null hypothesis said, well, we don't think the mean of the group is going to be any different from the mean of the population. It might even be worse. And in fact, what we see is that, well, we had a sort of a trivial increase. It went up 4 points, but in a ratio with the standard error, that gives us a z-score of 1.33. Tells us that the standardized difference between the mean of the group and the mean of the population is 1.33 standard errors. It had to be greater than 1.65 standard errors in order for us to conclude that this addition of these items would make an improvement in the scores. So the conclusion is that including these items doesn't improve the scores.